Good morning, Dr. Muhammad Aslisha. I'm Chen Yong Kang. So today me and my groupmates will present for the assignment of subject communication principle with the title Exploring the Impact of Noise on Modulation Techniques using AI Simulated Data. So in this study, we investigated the impact of noise on three common analog modulation techniques, which are amplitude modulation, AM, frequency modulation, FM, single sideband modulation, SSB, under different levels of noise. So by using MATLAB-based virtual experiments and AI simulated data, we analyzed the impact of additive white Gaussian noise, AWGN, at signal-to-noise ratios of 0 dB, which is high noise, 10 dB, which is moderate noise, 20 dB, which is low noise. The quality of demodulated signals are assessed using mean square error, MSE, bit error rate, BER, audio quality ratings with a scale of 1 to 5, and also signal clarity of poor, fair, good, and excellent. So based on the results we obtained, we found that SSB is robust in low SNR environments, outperforming AM and FM in noise resilience, whereas FM offers a practical balance between efficiency and noise resilience, and AM is easiest to implement but most vulnerable to noise, showing the highest BR and MSE. In modern communication systems, modulation plays a vital role in signal transmission. Just like AM is a modulation method where the amplitude of the carrier signal varies with the information signal, whereas FM is a technique where the frequency of the carrier signal is varied based on the input signal. An SSB is a refined form of AM that transmits only one sideband, either upper or lower, to save bandwidth and power. Besides, noise will degrade signal fidelity, resulting in demodulation errors and information loss. We use AI simulated data and field assessment metrics, and we aim to analyze each modulation technique's strengths and weaknesses in noise and explore trade-offs between noise resistance, power efficiency, and spectral use. Down to the methodology part, we use ChatGPT to generate the MATLAB codings, and we have 5 steps. The first one, single generation. A 200 Hz sine wave was generated as a baseband signal and sampled at 8 kHz to provide sufficient resolution for modulation. Next, the baseband signal was modulated using MATLAB's AM mod, FM mod, and SSB mod functions with a uniform 1 kHz carrier for consistency across modulation types, followed by noise injection. To simulate real-world conditions, AWGN was added to each modulated signal at SNR levels of 0, 10, and 20 dB. Continue by demodulated using AM demod, FM demod, and SSB demod functions, then normalize and compare to the original signal to assess fidelity. Lastly, demodulated signals were evaluated using the 4 assessment metrics as mentioned previously.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Azhad bin Sulaiman. Number metric B122310212. So today I will present about the result using ChatGPT for the MATLAB coding. So this MATLAB code simulates and evaluates the performance of 3 analog modulation schemes, AM, FM, and SSB, under different noise conditions defined by SNR, the signal to noise ratio. Values of 0, 10, and 20 dB. A 200 Hz test audio signal is generated and modulated using each technique, then passed through an AWGN, the additive white Gaussian noise channel, to simulate real-world noise. The received noise signals are demodulated accordingly, and both the original and recovered signal are normalized to ensure fair comparison. The script then calculates the mean square error MSE between the original and demodulated signal to assess the accuracy and robustness of each modulation method across varying noise level. So this is the coding. This is the parameter, the SNR, pre-allocate storage, loop through modulation type, modulated signal, loop through SNR, added noise, demodulated, normalized recovered signal, compute MSE. Then the code contains signals for BER calculation, log MSE per BER per SNR, and then visualize how MSE and BER vary with SNR across different modulation type. So this is the coding for context for BER, plot MSE, plot BER, And this is the output in MATLAB console. This is for the AM, FM, and SSB. So next, the discussion. There are three types of noise: low noise, moderate noise, high noise. For the low noise, the SNR is 20 dB, moderate noise 10 dB, high noise 0 dB. For the high noise SSB, the SSB shows superior noise resilience with the lowest MSE and VR and fair audio quality. For the AM perform worse with the highest MSE and VR and poor audio quality. For the FM performs slightly better than AM, showing moderate noise resilience. Next, for the moderate noise, for the SSB, this SSB continues to lead with a noticeable drop in MSE and VR, and the audio quality is rated as good. For the AM, AM shows better MSE and audio quality but remains behind FM and SSB. For the FM performs well, closely trailing SSB with similar VR and audio clarity. For the low noise SSB delivers the best results with the lowest MSE and VR and excellent audio quality. For the AM shows improved MSE and VR but still falls short of FM and SSB in fidelity. For the FM closely matches SSB in clarity and subjective quality. And that's all from me. Next, I will pass it to my friend Afi.
Assalamualaikum. My name is Afiq bin Amran. Let's begin with the discussion on overall trends and predictive insight. SSB or single sideband shows strong resistance to noise. It maintains high audio quality even at low noise signal ratios or SNRs. These make it ideal for long distance and bandwidth limited communication like the military or aeronautical systems. In contrast, AM or amplitude modulation is highly sensitive to noise. It performs poorly at low SNRs and falls behind FM and SSB. However, it does show some improvement at higher SNRs level. FM or frequency modulation strikes a balance between noise resilience and bandwidth efficiency. At higher SNRs, it approaches SSB quality, making it ideal for mobile and noisy environment. In conclusion, this study analyzed the performance of AM, FM, and SSB under three different noise conditions. There is 0 dB, 10 dB, and 20 dB. We used MATLAB virtual experiment and AI simulated data, focusing on four key evaluation criteria: MSE, BER, audio quality, and signal clarity. SSB demonstrated the highest resistance to noise, with the lowest mean square error and bit error rate. It delivered the clearest audio and is best suited for long distance and bandwidth constrained environment. FM performed consistently well at medium and to high SNRs, providing a good trade-off between quality and bandwidth. It is well suited for modern broadcasting and mobile communication. AM, although simple and widely used, is most vulnerable to noise, especially at low SNRs. It is best used in high SNR or legacy system where simplicity matters more than performance. Overall, this study highlights the importance of balancing quality, efficiency, and robustness when choosing the right modulation technique for different communication needs. Finally, let's take a look at potential future works based on this study. Advanced noise reduction. We can enhance signal clarity by using adaptive filtering and digital signal processing technique. Next is the miniaturized transceiver design. Develop compact and cost-effective AM, FM, SSB transceivers for embedded and portable communication system. Thirdly, the integration with emerging technologies. We can combine this modulation technique with 5G and cognitive radio to explore new use cases and address limitation. Next is the machine learning and adaptive modulation. We can use AI to dynamically switch between AM, FM, and SSB based on real-time signal condition to optimize performance. And lastly, smart antenna system. Implement intelligent antenna that boost signal strength and improve reception quality across all three modulation types. This advancement aim to make modulation technique more flexible, efficient, and adaptable to future communication changes. Thank you.